this video, we're going to be taking a look as to what is a chemical equilibrium and what is the math associated with equilibrium constants. Why would this be useful to us? Let's consider a simple reaction where diatomic hydrogen and diatomic iodine react to produce hydrogen iodide. At the beginning, what we're going to notice is that we have lots of hydrogen and lots of the iodine. We don't have any hydrogen iodide as yet. In order for the hydrogen and the iodine to react with each other, from our unit on reaction rates and our study of collision theory, we know that the hydrogens and the iodines will have to collide and bonds will have to be broken and reformed. We can see that as the hydrogen and iodine move together and collide into each other, that eventually the bonds will break and we will get hydrogen iodide combinations being formed. Now eventually the amount of hydrogen iodide will start to increase. And once we have enough of these hydrogen iodide combinations, it stands to reason that the two of them will be able to bump into each other and eventually start to react themselves. If enough of these guys build up, that we actually produce lots of hydrogen iodides, and they actually start to be able to collide together. We could have scenarios, I can grab them at the same time here, we can have scenarios where hydrogen and iodine start to reform, and the reverse reaction starts to take place. So at the beginning, we see that we have lots of hydrogen and iodide, and so the forward reaction is quite fast, and we have no hydrogen iodide. But as the hydrogen iodide concentration increases, eventually the reverse reaction takes place, and hydrogen and iodide themselves start to reform. An interesting thing happens because we're going to reach a position where every time one hydrogen and iodine react to form hydrogen iodide, another set breaks down. And you'll notice that we end up with a situation where the amounts stay equal. I have, in this particular reaction, one each of the hydrogen and iodine and two of the HIs. But I can see that if the rates of the forward reaction, where HIs are produced at the same rate that I's and H's are broken back down, those constant amounts are unchanging and constant, and that is an equilibrium. So in this reaction, which is reversible, and this only happens if reactions are capable of going in both directions, then the conversion of reactants to products and products to reactants is going to happen at the same time. Because this is happening at the same time, we can get an equilibrium. And what's equal here is the rate of the two opposing reactions, not the amounts. In the example that I just did, we didn't have the same amount of product as reactant, but the rate of forming product was equal to the rate of forming reaction. And that's a really important concept to realize. What is equal in equilibrium? Well, the answer is rate. In this graphic, we can see that my forward reaction, which had lots of hydrogen and iodide, forming hydrogen iodide, slowed as my reactants got used up, until eventually the rate leveled off. We also saw that although initially none of the reverse reaction happened, eventually over time it sped up and it sped up and it sped up until that rate equaled off. At the point where the two rates were the same, the rate of the forward and the rate of the reverse, we were at equilibrium. Now this is not necessarily true if we were to graph amounts. If we were to graph amounts, we might notice that the amount of hydrogen and iodide, although high at the beginning, eventually levels off to the point where the amount no longer changes. And the amount of HI, hydrogen iodide, although initially nothing, would increase and increase and increase until its amount also leveled off. So this blue line could represent the hydrogen iodide line. You'll notice that at equilibrium, the amount of HI is unchanging. The amounts of hydrogen and iodine are unchanging. equilibrium the concentrations of my reactants and my products. Remember, square brackets means concentration is constant, but the rates of the forward and reverse reaction are equal. I can often see that an equilibrium has been reached by noticing no further change in a reaction. We've probably inaccurately considered the reaction to have stopped at that point, but in reality, we've more likely hit an equilibrium scenario. Consider a system where two clear gases react to make a brown gas. At some point, we would notice that the color stopped changing. It is not likely that we've used up all of the clear and changed it to the brown, but that at some point, the reverse reaction has kicked in, and somewhere in the middle, we would have sort of a lightish brown colored gas that was staying formed. When we no longer see change, we know we are at equilibrium. Now, the neat thing about the math for this unit comes from a law called the law of mass action. And the law of mass action says that if we have an equilibrium reaction, then I actually get to use the balancing as my coefficients. So I'm going to get a constant called an equilibrium constant. K means constant and EQ stands for equilibrium. And it's going to put the rate of the reverse reaction over the rate of my forward reaction. And I know that my rates are based on concentrations. And since it's for the same reaction, they both get a rate constant, but the rate constant would be equal to each other, so that factors out. Based on the above reaction, which should really be written with two-way arrows to represent an equilibrium that is heading in two directions at one time, we can follow this general formula. The Keq for any equilibrium reaction then will be the concentration of the products over the concentration of the reactants to the order of their coefficients, which is just the numbers from the balancing. So for this formula, the products, which is everything on the right, would be the concentration of HI over the concentrations of H times I to the order of their balancing. So we can put a square by the HI and to the order of 1 for each hydrogen and iodide. And this can be written for any equilibrium equation. So for a simple reaction where I have letters standing in place of reactants and products, I would put the reactants or the products on the top, C and D, in their concentrations, so that's square brackets, to the orders of their balancing, and the reactants on the bottom. Now, one thing to remember is that we'll never include liquids or solids in Keq calculations. We're going to use gaseous form or aqueous form only. Gases and solids are defined as having a concentration of 1. And I sometimes see Keq calculations where they've written concentrations in and then identified them as liquids or solids. If you see questions like that, then just cross them out of the equation, because timesing and dividing by 1 won't change your answer. And they've really just put them in to see if you're paying attention to the states. When I calculate this, though, the position that we get, the Keq, tells me something interesting. It tells me something called equilibrium position. An equilibrium position tells me whether or not my products or my reactants are favored when I hit equilibrium. Remember, equilibrium doesn't necessarily happen in the middle. The equilibrium can happen at any point. Using the above example, if as soon as A and B react to make C and D, that equilibrium immediately sets up, that it immediately starts the reverse reaction, then at the point of equilibrium, I'll have lots of A and B. My denominator will be very, very large, and my numerator will be small. So in a case like that, the Keq will be less than 1, and my reactants will be favored. Some equilibria, however, don't happen until large amounts of products are formed. At that point, there's hardly any of my reactants. My numerator is quite large. When this happens, the Keq value is greater than 1. A Keq greater than 1 tells us about an equilibria that favors the products. Knowing whether or not an equilibrium sets up right away as soon as a little bit of products are made, or doesn't set up until you have a lot of products, allows us to make decisions about how to manipulate that chemical reaction to get the results that we desire. Consider again a version of the hydrogen iodide reaction. In this reaction, I have hydrogen ions and iodide ions reacting to make hydrogen iodide. We can see that as soon as hydrogen and an iodine reacts, the amount of hydrogen and iodine go down, and we know that equilibrium could set up at any point. We could continue this until we have many hydrogen iodides and hardly any H and I's left. If the equilibrium hits at this point, you'll notice that we have 4 HIs and 1 each of the hydrogen and iodine. My Keq is going to be the concentration of my HI over the concentration of my hydrogen ion times my iodide ion is going to be 4 over 1 times 1. Will give me a value of 4. If this is the point of my equilibrium, then every time a hydrogen and an iodine react to form an HI, another one breaks down. You'll notice that I still have 4 HIs and 1 H of each, the hydrogen and the iodine. Another one forms, another one breaks down. The amounts stay constant. The reaction continues to happen. Every time 1 HI is formed, another one breaks down. So when we have a value like this, where the number is greater than 1, that's telling me I'm going to have lots of products at equilibrium. But it is also possible that the equilibrium could have set up immediately. Suppose we have this scenario where my equilibrium sets up almost immediately. At this moment, we could see that as soon as hydrogen and iodine form HI, we might be at equilibrium. I can count right now that I have 4 hydrogens, 4 iodides, and 1 HI. In order to be at equilibrium, we are saying that every time 1 hydrogen and 1 iodine connect, another one breaks down. You'll notice we're still at 4 hydrogens, 4 iodines, and 1 HI. Again, if we're at equilibrium, every time 1 hydrogen and 1 iodine connect, another one breaks down, 4 to 4 to 1. In this case, the concentration of HI is 1. The concentration of each hydrogen and iodine is 4. 1 over 4 times 4 is 1 over 16, is 0.0625. We have a Keq value being much less than 1. This tells us that the reactants are favored at equilibrium. That means when we hit equilibrium, we have more reactants than we have products. In this example, with gaseous carbon dioxide reacting with hydrogen to form carbon monoxide and water, we have equilibrium concentrations calculated as given. We put the reactants on the bottom and the products on the top. So we're going to have the concentrations of carbon monoxide times that of water over carbon dioxide and hydrogen. In this case, I'm allowed to use the water because it's taking place in the gaseous form. Substituting the numbers and doing the math gives me a value of 2. This tells me that in this reaction, the products are favored. A shorthand way of indicating where the equilibrium position lies is to make the arrow bigger in that direction. Because the products are favored at equilibrium, my arrow pointing in that direction is often will be drawn larger than the arrow pointing in the reverse reaction. Again, the reaction doesn't stop, but continues. It just continues to the point where these concentrations are higher than these concentrations, but they will remain constant at equilibrium. This would be a great point for you to try writing equilibrium reactions and calculating Keq values. Pause the video here. First, write your equilibrium expressions, then substitute and solve for the value. Once you think you have gotten as far as you can, press play and check your answer. In the first example, The equilibrium constant will be products over reactants. I only include the K2S and the Na2S because my sodium nitrate and my potassium nitrate are in the form of solids. Solids and liquids are not included in equilibrium expressions. So, like I warned you earlier, these numbers are here only to see if you're paying attention. Substituting then, the concentration of K2S is 0.032 and for Na2S it's 0.058. Doing the math, we get a value of 0.55. Because this value is a value less than 1, we can say that the reactants are favored in this equilibrium. And so if I had proper equilibrium arrows, I could draw this here with the larger arrow pointing in this direction. Try now to figure out the values asked for in the second equilibrium. In this case, I've given you the Keq and asked you to solve for a missing variable. To write the equilibrium expression, we're going to put products over reactants to the powers of the coefficients. My products are always on the right. So we're going to have the concentration of HI squared over my reactants, the concentrations of H2 times I2. Remember, this is multiply and divide. There's no plus minus in the math. Substituting. We've been told that Keq is 32, so in place of Keq, I put 32. HI's concentration is 0.4. Don't forget to square it. H2 is our unknown, and I2 is 0.05. Rearranging to solve for the concentration of hydrogen, we find that the concentration of hydrogen gas then will work out to 0.1 moles per liter. To practice concentrations and calculations with equilibrium situations, read Chapter 17 in your textbook and do the questions as indicated from pages 600 to 626. Also, in your workbook, you'll find a worksheet entitled Equilibrium Constants that will give you practice, both calculating equilibrium constants and rearranging the formulas to solve for a missing variable.